Thanks very much. So good morning again, everybody. My name is Christine Träger-Chatterjee. I work at EUMETSAT as a training officer. I am responsible for all the training activities we manage in the area of marine and climate, and I'm also taking over the land applications from a colleague. This webinar today, or this information day, is about a data cube that EUMETSAT has produced. It is a data cube for drought and vegetation monitoring. This is a prototype. That means it's the first data cube EUMETSAT is providing. You may have realized that there is no big announcement on our webpage about this cube yet, which is for a reason, because this is an experiment and a prototype. We still need to learn a whole lot, and we already have learned a lot, but the most important step is starting exactly now. Because we would like to explain to you what we have done, and we would like to hear from you in the next few months if this is useful for you and how we could do even better. So a prototype, and today is the information day to get it started. And may I just ask, Regina, can you see my screen? I'm not so sure anymore.
Yes, we can see it.
Okay, thank you. So what will happen today? First, I will give you a bit of a background on what this cube is and why we have even built it, where to find more information about the cube. After that, we will introduce you to the variables that are provided in the cube. And with that, I have a lot of help from many colleagues who are experts on the data sets that are provided here. Then we'll have a coffee break at around 11-ish. And after the coffee break, we're going to go into a little bit more into details on how to access the data cube. And we would like to introduce you to a tool that we think is very useful in working with gridded data records. And then we will hear from Meteor Swiss a presentation on climatological drought monitoring in Switzerland using satellite products. They have done a feasibility study without knowing that in parallel we were planning to provide a cube, but still I think this is a very interesting project, and I hope that we could trigger even more interest and ideas on how satellite data can be used in drought and vegetation monitoring. And we will then do an introduction to the exploration phase, how we think the exploration phase will work and how you can participate in that exploration phase. And towards the end, we'll wrap up with a final question and answer session and the feedback from your side. Questions and answers are always welcome. For questions, please use Slido. If you go to slido.com and enter the event code DVCube. And you can also download the app on your smartphone and enter the code DVCube. And you can ask your questions in Slido, and we will go back to the questions regularly to go through them and answer them here in this webinar. If you have any technical issues throughout, if you cannot hear us anymore, if you cannot see the slides, then please use the Zoom chat to ask or to let us know. And my colleagues in the background will do everything to help you out as soon as possible. But for questions on the content, please use Slido. All the information on the drought and vegetation data cube is available on a Moodle page that we have created. And Regina, if you mind pasting the link into the chat, thank you. You can go there and you'll find all the information that we can provide to you about the cube there. Also, after this information day, we will upload all the recordings and all the slides that have been presented today onto this page. And to start with, I have a question for you, just to give me a bit of an insight or a bit of an idea of who we are talking to today. Is, have you ever worked with satellite data before, or is this the very first time? If you go to Slido now and go to polls, then you see this poll, and please just answer with yes or no and send your reply, and we can see that live here on the screen. Regina will pull that up. That's just a little background information for myself and for my co-presenters and instructors today. Regina, do we already see some results?
Yes, 1 second.
Probably we need to give a bit more time, so the poll is still open. You can take your time and go to Slido, answer these questions. Can you share the results so everybody can see it? Or do I need to stop share? Okay.
One moment. Can you see it?
Yes, I can see it. Can everybody else see it? I suppose so. Yeah, so 33 people have answered. Okay, the vast majority have worked or has worked with satellite data before. And I was not sure if this was the case. So yeah, I hope the presentation that I've prepared is not below your expectations, and that it will still be useful for you. But you be sure you can dig as deep as you like into the details that we'll provide for you. Okay, first of all, this is the cube has been created and provided by EUMETSAT. EUMETSAT is an intergovernmental organization. We have at the moment 30. So sorry, you cannot see my screen anymore. I just realized, yes. Sorry. Yeah, so at the moment we have 30 member states. Our tasks are basically to take care of all the meteorological satellites in Europe, basically for our member states. And this starts with the development of the satellites, with exploring the needs, making sure the satellites is built in the way that are needed, that are sent up into orbit, and that they are operated properly, and to make sure that the data are available in time for the numerical weather prediction, but also for climate monitoring, for example, to detect global climatic changes. And in addition to that, we form together with ESA the space segment of the Copernicus project of the European Commission. So how can we provide you with data that are relevant for drought and vegetation monitoring? This requires quite some people and quite some effort. So satellite data satellites satellite measurements are translated using retrieval algorithms into geophysical variables. This means, of course, you need smart people and algorithms, but also computing power to produce these large data records. And what we will be talking about today is purely geophysical variables. We will not talk about the radiances provided from the direct satellite measurements, but it will always be the interpreted geophysical variables. We are not doing all of this alone. We collaborate basically we build a family together with our the EUMETSAT satellite application facilities. You may have heard about that or not, I'm not sure. So the satellite application facilities are a network of centers of excellence, basically. So each center or each SAF has specialized in a certain topic to retrieve satellite data for. So at the moment we have 8 different SAFs, and today we will hear more about products from the SAF for land surface applications, from the SAF for climate monitoring, and from the SAF for hydrology and water management. Each SAF is a consortium of entities from different member states. So they have provided quite some variables and data records of these variables to the cube, but we were not only using satellite data and not only using variables provided from the SAFs, but we also used data that are provided from the ERA 5 reanalysis provided by the ECMWF, and precipitation provided from the Global Precipitation Climatology Center. And you will hear more about that in a few minutes. The Drought and Vegetation Data Cube. What is the issue? Why did we think there was a need to provide a cube? Well, I think there is no doubt that out there are many great Earth observation data that could be used to monitor drought and vegetation. But there are also many providers, and thus there are many ways of accessing the data, many ways of how the data are provided to the user, so many data formats, for examples. And in the trainings that EUMETSAT has delivered for climate applications, we realized that these different ways of accessing data, handling different formats, is for many users a big barrier to access the data and to use them in a way that it really adds value to their work. So the idea is bringing the data closer to the user. Analysis-ready data is a key word of these days. So the idea was to build a cube that brings together data also from not only from different SAFs, but also from other data providers, as I mentioned. So we did this, and the data cube, we decided to start with a cube for drought and vegetation monitoring. So we were looking, what do we have in our portfolio? What do the SAFs have in their portfolio that is useful for drought and vegetation monitoring over longer periods? And then we were contacting the SAFs, and they were all very willing and very supportive for this project. So we got a company who took the data and put it all into a CF compliant NetCDF4 format. And we were giving them a common data model where they should bring all the data into. So the data that are provided for you in this cube are all on a regular latitude, longitude grid, and we use a common metadata definition. And I would like to emphasize again that this is a prototype. It's a prototype for us. It's also a prototype for you, and you are the most important player in this whole project, because we would like to learn about your needs, which is why your feedback to us is so important. So at the end of this project, it would be really great if we could have a feedback also throughout the month, anytime, telling us, are cubes even useful for you? Is the format in which we are providing it to you, is this appropriate? Is the data model that we use appropriate for your work? Is the way we provision the cube to you appropriate? What will be best for you to work with? How can we serve you even better? Anything that you think could be a useful constructive feedback for us is very much appreciated, and you will learn later on how we envision to manage this feedback. So now, what is actually in the cube? You may have seen this table before. So in the cube, we have a few solar radiation parameters. We have land surface temperature, reference evapotranspiration, NDVI, fractional vegetation cover, leaf area index, photosynthetical, the fraction of absorbed photosynthetically active radiation, soil wetness index in the root zone, precipitation, and 2-meter temperature. Most of the variables are provided by satellites. precipitation is from in situ, and 2 meter temperature is provided from reanalysis. We have taken the data records from their start. So whenever they started to become available, we have taken it to then. And the data cube ends by definition at 31st December 2020. Except for 2 meter temperature, this was taken from analysis, and we had to stop in October 2020 because December 2020 would have been available after we had to close the project. So at some point we needed to say, okay, we take whatever is available then. That doesn't mean that it always needs to stay like this, but this is as we have decided for in terms of the data cube. The data are available in different spatial resolutions. You can see that here, and also in different temporal resolutions. We can provide you with daily, monthly, hourly, and 10 daily resolutions. And you will hear more details later from the data experts on this. The cube is available for the cutout of Europe. And as I said, on a regular latitude longitude grid in CF compliant NetCDF4 format. To access the cube, we need to please ask you to enroll to the DNV cube, the Drought and Vegetation cube exploration phase. You can do that also on the Moodle page. This is because we need a minimum of information about you and who you are. So I would like to ask for your understanding here. And I will explain also later how you can enroll to this exploration phase that also then gives you access to the cube itself. This is the same table, with a bit of additional information. So here we give you information on where is this data coming from, who's the data provider. And you may notice here that the temporal coverage is different between these two columns, between climate data records and interim climate data records. On the Moodle page, you will also find a short video that explains in a bit more detail the difference between climate data records and interim climate data records. Here, I'll give you a short introduction into that subject. So basically, the distinction is that climate data records usually end quite some time before present, only by coincidence, at least for the satellite data. They may just have been updated. So this is the temporal coverage is divided into climate data records and then the interim climate data records, which fill the gap between the end of the climate data records and present time. Why do we have to, or why do we distinguish between climate data records and interim climate data records? This is what I will explain you very briefly here. So satellite measurements are acquired continuously all the time. A retrieval method is applied to it in order to translate the satellite measurement into a geophysical variable. This happens continuously. But for climate monitoring purposes, we need to look at a lot of data. So ideally, a few decades we would look at. This is nowadays possible with satellite data, which is great. But this also means that we have to integrate measurements from different satellites, because the satellites is usually not up in space and operational for several decades, but only for several years. So there are updates to the sensors. New sensors are brought into space, and new algorithms are developed as well. And this all needs to be homogenized when providing climate data records. So we need to make sure that we are comparing apples with apples, also if the measurements are 20 or more years apart from each other temporally. So this has been taken care of when producing climate data records. And also we use one and the same algorithm to provide climate data records. The interim climate data records, as I say, fills the gap between the end of a climate data record and present time. So it's using data as they come in all the time. or the retrieval is applied to the data as they come in continuously, but the same algorithm that is applied for climate data records is also applied to the interim climate data records. In short, one could say that the climate data records usually is the best available quality that can be provided for you. The interim climate data record cannot be expected to be as of the same quality as the climate data record, but the closest possible or the highest quality possible at the time being. For more information, I would like to refer you to the little video that I've prepared and that is available on the Moodle page as well. So what is actually in the data cube and what can you see when you open it, when you browse the catalog? So first of all, the first part of the folder name always gives you the name of the provider of each data record. So you see the different SAFs, ACMWF and the GPCC. You can see the type of the data records, if it is a CDR or an ICDR, the difference I've just explained briefly. The variable that we are looking at, the name of it, and then the MDH gives you the temporal resolution of the data record. Is it monthly, is it daily, or is it hourly? For more details on the variables, you can also find everything hopefully that you need on the Moodle page. So we've provided fact sheets for each of the variables, which give you a quick overview on the most important information you need to know when working with the data. But we also provided you with what we call a full guide with more details and links to the relevant documentations of this data records. How can you get to this page? So Regina has pasted the link to the chat already. Maybe we could do this again. But if you go to EUMETSAT, to training.eumetsat.int, go to the menu courses, land applications, and then select the data cube information page. This is open access, available to everybody. You can just click on it and get into. Up until now, we will go into the details of the variables right after this, but up until now, are there any questions?
No.
Okay, good. So another reminder, if you have any questions, please use Slido to raise them. There was a question on the link for the Moodle page. I think this is available now in the chat
Yes.
again. Good. So we can now go into the details of the variables on the drought and vegetation data cube. I will start with the solar radiation parameters and the 2 meter temperature, but 2 meter temperature, I think I do not need to explain really much. So it's a temperature 2 meter above ground, and we have taken it from the ERA 5 land reanalysis, and that's all I have to say about this at this point. I think we need to have you probably appreciate a closer look at what else is available. So we provide you global radiation. This is something that is retrieved from satellite, and it's provided by the CMSAF. And it gives you the total amount of solar radiation reaching the Earth's surface. This can be very accurately derived from surface observations, because satellites can so this is a variable that is very close to the satellite measurements. So a satellite can detect clouds very well, which give you the bright regions during daytimes. And because we know the clouds, we can also retrieve the clear sky solar radiation very well, which is then an input into the radiation transfer calculation. And so it is possible to retrieve the solar radiation that reaches the surface of the Earth. From this, from an end, and we can also detect because of this information we have the direct normal radiation. That means that global radiation gives you the total amount of solar radiation, direct plus diffuse, that is reached that reaches the Earth surface. The direct radiation, in difference to global radiation, is only that part of radiation that is not scattered throughout its way through the atmosphere by clouds or aerosols or the like. From this direct normal radiation, it's also possible to retrieve the sunshine duration of a day. So here, the sunny slots are counted and put into relation to all slots over a satellite measurement during daylight, and this is then multiplied by the length of the day. And the sunny slot is defined as a slot where the direct normal irradiation is larger or similar than 120 watts per square meter. And the day length is defined as the period when the sun elevation angle is larger than 2.5 degrees. So we provide you solar radiation parameters, global radiation, direct normal radiation, and sunshine duration. Are there any questions on?
Yes, we do have.
No? Yes.
Yes, should I share the screen?
Yes, please.
Can you see it?
Yes.
So these are the recent questions. Would you like to start with this one?
Okay. Have you on this DNV cube targets for latency to answer questions? I am not sure what is meant with this question. Can the person who asked the question please raise their hand so we can give you the microphone?
Hello, Mikko Strandov here.
Hello.
So this is a technical question, but in general, I think when this was the part where you have the technical like data cube, let's say presentation, so I thought this is the place to ask. Just in general, I think this is a very useful exercise to have different sources of data available in a similar fashion. But especially, I think the point is about subsets and then how fast you can retrieve them. And just, let's say, the Finnish Met Institute, where I work, we do this with our own server systems. And there, I think one of the key things we learned is that you have to have a pretty fast kind of how to solve a request to be able to then start sending data out. That latency is a very kind of key factor of how popular a service becomes. So did you put for yourselves any of those kind of latency like targets?
No, we don't have targets so far. We are, you hit the nail really. So the data, and you will learn that also later, is provided to you on a thread server. And I will explain after we have gone through all these variables, the functionalities that you can use with the thread server. But this is where we definitely have to learn a lot, and we also had to solve quite some issues. And if FMI has experiences with that, we would be very happy to discuss it with you. And I'm sure that this will be a question that we'll discuss heavily also with our IT colleagues.
Okay, happy to help. And we can get back to it then in this later part.
Yes, okay. Thank you.
Thank you.
Is there a plan to provide... Ooh, sorry, now I lost the question. The main goal is to have fast delivery in both latency, download speed for subset retrieval. The latency, I think that's just what we've discussed now, right?
Yes.
Yeah.
There was another question, but I don't know why it was taken out.
It just disappeared. subsets, yes, that goes into the same direction. So you will be able to subset the data. You will be able to subset variables. You will be able to subset the region and also you will also be able to subset the time you're looking at. Is there a plan to provide higher temporal resolution in another version of the cube? So, for example, hourly for solar radiation. Interesting question. That all then depends on what exactly is needed and what the data should be used for. Is it really to do near real-time monitoring? Then I think we are talking about a different thing. Or is it to do really monitoring for, changes in the environment, so climate monitoring? And then it also depends on what is available. But yes, we are very interested in learning what is useful for you and what you need. And then it's up to us to discuss internally what is possible and how. Okay. If I am not wrong, I think we have covered all the questions that are there at this moment.
Okay.
And then we can continue with having a look at the precipitation data that is provided in the cube. And I hand over to my colleague, Mark.
You can see my presentation now.
Yes, we can see it.
Yeah, it's on the generation of the global of the monitoring product, which is added to the data cube. I can. That's the next slide. So first, the database or the data which are used for this data set. It is based on CLIMAT and SYNOP data. CLIMAT data, or maybe I start with the SYNOP data, that are the observations taken at the weather stations, manned or automated stations, and used, for example, also for numeric weather prediction and warnings. It contains also a section about precipitation, and that is used in this data set. And the other data are used are the CLIMAT data that are monthly summaries from stations provided by the National Meteorological and Hydrological Services. And they've done a quality control at their own and then provide the data with some delay. The data are run through a semi-automated quality control. And due to the delayed availability of the CLIMAT data and the effort we have with the quality control, the data set is available with a delay of 2 months in principle. So interesting is a quality control. It's based on 4 steps. The first step is a consistency check at the station level between CLIMATs from we receive. We get the CLIMATs via the WMO Global Telecommunication System, and that's organized by several centers, and we receive the same, in principle, the same message from several centers. And this should be identical in theory. But in reality, there are sometimes differences because of not provided or forwarded corrections or whatever reason. And then we compare the CLIMAT messages we receive from 3 independent centers and decide which is the correct one. After this decision, which is in human interaction, the data are loaded to our data bank. And during this process, we do a statistic check against the monthly totals if they are below the 1% percentile or above the 99% percentile. This is the percentile is calculated from the station time series, or if that is not available, from the grid time series. And all data which are flagged in this stage are checked manually. The third step is what we call a first analysis. So we do a gridding of all of these station data. and compare the gridded data with the long-term means of the grids. And then we calculate anomalies and if have some procedures to classify them. And if they are above a certain threshold, they are flagged and yes, have to go to an additional manual check. And on principle, so we have, or on average, we have to check around 7% of all these data manually. And at the latest step, we have colleagues who go via a map with all station observations around the globe and check for spatial consistency of the data. And after these quality control steps, the final version of the product is generated. So the grids are produced by means of a modified sphere map scheme. So it's not the original one, which is described in the paper by Wilmot, but there are some publications from the GPCC where we describe the modifications we've done. So it's a geometric interpolation scheme. And we use at minimum for each grid cell 4 stations and a maximum 10 stations. So that means if in one station is only one, in one grid cell is only one station, we use 3 stations from other grid cells. And in case there are more than 10 stations in one grid cell, which is not the case, we would cut at the 10 stations next to the center of the grid cell. The number of 10 stations in a grid cell, you have to keep in mind that we run the interpolation at 2 levels. We first run it on a subgrid of 0.5 degrees globally. And then after that, we calculate the final 1 degree spatial resolution from the subset to get a better areal mean estimation. So for the sphere map scheme, it's a geometric interpolation scheme which combining an angular and an inverse distance weighting. First, for the inverse distance weighting, as you have a grid point, and here in this example 4 stations, and as nearer the station is to the grid point, as higher is the value that the station gets. So the station 1, which is nearest, has the highest weight to the grid point value, and station 4 has the lowest one. Then an angular weighting is also introduced in this interpolation scheme. That means you have a grid point here, and here 2 stations which are more or less alone, and you have here 3 clustered stations. And the angular weighting reduces the weight of the 3 clustered stations in comparison to the single stations here. And the last point in the, or last procedure in the sphere map scheme is that it computes gradients between the observations. So you have a grid point here and one again for stations, and the bars above the station point should indicate the precipitation amount measured at the stations. And if you would do an manual interpolation, you would assume that the grid point value could be higher than the observed values. And sphere map takes also the gradient between the stations into account and can produce slightly higher values at the grid point than from the observations. So that's for the interpolation scheme. And for the monitoring products, the precipitation data set used in the data cube.
Are there any questions on the precipitation data records to Marcus?
Yes. 1 second.
Okay, Marcus, let's go through. What does the acronym SPE remap represent and mean?
Sphere map is a spherical implementation of an interpolation scheme from developed by Shepard in 1968. So it's no special acronym, it's only a name for this interpolation scheme.
Okay, I think the next one is rather one to me. Are there plans to incorporate rainfall satellite derived data sets as TOMSAT, CHIPS, or CMORPH to the cube? We have not thought about that, but that does not mean that it is included. So it's entirely possible that there will be a cube in which other precipitation, also satellite retrieved data records will be available. Quality control for precipitation data, at what temporal resolution is that, daily or monthly?
That is at very a large number of temporal resolutions. So the climate data are monthly data, that's then on a monthly basis or for monthly totals. But the SYNOP data, which are also used, has different temporal resolutions from 1 hour to a daily. And we have done an automated quality control on the original totals, so and on the daily totals and so on. And finally, also on the monthly totals, we compare or calculate from the SYNOP. So it's on various temporal resolutions we do the quality control.
Okay. The next question is if there are plans to provide a data cube also for Asia. So we have started with basically our prime audience, which is Europe, but that does not mean that we will not provide data cubes covering other areas. That depends a bit also on what kind of feedback we get and also requests from the different regions, what is needed and what not. If you're interested in that, then yeah, please let us know if this is helpful, and we also need to see how the requests can be triggered and how we may be able to fulfill it. Yeah, that's my answer to this. I see no other questions at the moment.
Screen up. So I had a bit of issue with full screen earlier when I tested it, so I'm going to present it like this. But yeah, as Christina said, I'm in charge of the root zone soil moisture data record at ECMWF with Patricia. And so essentially the way it's produced is illustrated in this flow diagram. We assimilate scatterometer data from 1992 to 2020. So in the 90s up to about 2006, that comes from the ERS instruments. And then from 2007, we assimilate ASCAT A and B. As well as that, we also assimilate screen level observations at 2 meter. And we use a simplified extended Kalman filter to essentially assimilate these observations into the H-Tessel land surface model. And this model is forced by the ERA 5 atmospheric reanalysis. And so the process here with the extended Kalman filter in the model, the soil moisture is performed in volumetric units, but we want to basically output it as a liquid soil wetness index. So it's quite consistent then with the ASCAT observations themselves. So we perform a post-processing step using the frozen content and also the soil texture, basically to convert it from this volumetric to liquid soil wetness index. And the liquid wetness index, essentially 0 means that there's residual soil moisture, so no liquid content, and 1 means it's saturated. So we produce the H141 climate data record from 92 to 2018. It's all valid at 00 UTC daily. And then the interim data record is an extension essentially of H141. So really exactly the same thing, but extended from 2019 to 2020. And we produce this over 4 layers. So we have 4 variables that you'll see if you go into the catalog. So you have SWI1, which is 0 to 7 centimeters depth, SWI2, which is 7 to 28 centimeters, SWI3, 28 to 100, and then a very deep layer for SWI4. So the first 3 are broadly representative of the root zone, and this is all at 0.1 degree sampling. And you can find more documentation online or through the Moodle page. So these plots here I just put on to illustrate it. So the top plot is just the soil moisture trend over autumn, so the mean trend from September to November from 1992 to 2020. And you can see that it's quite interesting, some interesting patterns, like, for example, a wettening over very high latitudes and the drying of the soil moisture over mid latitudes. So I don't have really time to go into details about it, but you can definitely see there are some trends there. And here you can look over Europe and you can see that the trend is clearly drying over the autumn months, indicating probably climate change might be having an impact there on the soil moisture conditions. So yeah, that's it for me for now. So thank you. And I'm happy to take any questions.
Thank you very much, David. I'm just checking on Slido. Are there any questions there? Yes, I can see one question, Regina, if you could put it up. Oliver's asking, have you validated soil moisture data for different vegetation cover types? E.g., what is the influence of forest biomass on satellite data and thus the retrieval?
Yeah, that's a good question. So we did an in situ validation using various networks from the International Soil Moisture Network, which you can find, a database, sorry, which you can find online. And I'm not sure about forest data. There probably were some observations in forests. Generally, I think if it's very heavily vegetated, the signal is not so good. So probably we would expect the accuracy to be less, basically, because the ASCAT observations themselves are less accurate in forest types. But I haven't looked at that specifically and compared it with the other types. But what I can say is that we use a range of networks, Snowtel, for example, which is in quite mountainous areas, SCAN, USCRN in agricultural areas in the US. And most of them are not in forest areas, to be honest. But for the other vegetation types, it tends to be quite good. It's quite robust.
Okay, thank you. What is the source of the soil texture map, and what is the native resolution of the map?
That's a good question. The soil texture map. I can give you the link for that. But yeah,
I assume that's probably covered in the product user manual.
It is, yes, indeed. Yeah, you can find it in the algorithm theoretical baseline document. We have the soil textural map, so you can find it there.
Yeah, so all these documents, the product user manuals, the ATBDs, which is the exact description of the algorithm, and validation reports are provided on the Moodle pages. So you should be able to find them there. And if this does not answer your question, then please do not hesitate to get back to us. How do you produce soil moisture at different depths?
So basically the land surface model is integrating the soil moisture at these different depths. So using the model basically is how you get from integrating the surface observations, which come from the scatterometer and the ASCAT, and getting this observation into the root zone. So essentially the land surface model is the dynamic way of doing that. And the data assimilation algorithm provides a way of integrating these observations into the land surface model. So you use the observation errors from the observations to give them a weight, depending on how accurate they are. And you also have the background errors, which is related to the land surface model, to give a weight to the land surface model. And the combination of this information together with the dynamics of the land surface model gets the information from the observations into the deeper layers.
Okay. Next, sorry, Oliver, I skip yours. I get back to it a bit later. Did you compare your trends with the ERA 5 soil moisture outputs? And is there an improvement in reproducing observations?
So yes, I have looked at ERA 5, and there is definitely some similarity with ERA 5 for the trends. So ASCAP and ERA 5 are not the same. They don't actually produce the same trends, funnily enough. There are some areas in Europe, for example, where ASCAP, the signal, is not really producing this negative trend, which is quite interesting. So it suggests that some of the trends are actually coming from ERA 5. So that's something that we want to look into more detail, also to look at any biases that might be in the ASCAP observations so that we can improve them and work with the people that produce the soil moisture products themselves.
Okay, thank you. And here's already coming an answer on the soil texture map that is used. You can see it on Slido as well. Go back. I like that. Thanks very much.
Thanks very much. It's helpful.
And then there's another question. Forest data might be good enough to at least get the seasonality of soil moisture.
Yeah, probably. I think that you've got, I mean, obviously the land surface model will also pick up the soil moisture in forest areas as well. So even if the ASCAT observations are not so accurate, you would still get anywhere that's less accurately measured by the observations. The land surface model can still do a pretty good job.
Okay.
That's something to bear in mind as well.
Okay. Okay, I am aware that there are probably a million further questions, but at this point I'd like to interrupt this here so that we can have a chance to have a 5-minute break before we continue. But I would like to make you aware that we will have a short course specifically dedicated to this variable, to the root zone soil wetness index, on 16 June, where we will go into more details, and we'll also have the time to go deeper into the questions that you may have. And if there's anything in the meantime that stops you from working with the data record, then of course please use the Moodle forums to raise your questions, and we will answer it there. But how this works, I will explain to you later. And now I suggest let's take a 5-minute break, and let's get back here at in 5 minutes, so we can continue at 10:30 sharply with having a look at the land surf parameters. So then we go more into the vegetation.
Okay, good morning, everyone. So I'm presenting the land surface temperature that is contained in the data cube. So this is radiometric temperature. So this is what we would measure if we touch the surface, corresponding to the thermal emission of a very thin layer of the land. So we to derive this product, we use a generalized split window formulation, where the land surface temperature is estimated from a linear combination of brightness temperatures measured in the 2 split window channels, and assuming the emissivity, spectral emissivity, is known. Of course, we have to correct the atmospheric effect to retrieve this variable. So the LST is retrieved since 2004 at the frequency, at the temporal frequency of Severi on board MSG. On the data cube, you will find data every hour. And here is an example of LST, and you see there are gaps in the data. This is because as we are retrieving this variable from infrared measurements, we cannot see the surface when we have clouds. Actually, we are now distributing also a new product that is available from March 2021, that is for all sky conditions. And maybe this can be also distributed in a future edition of the data cube. This slide highlights the difference there is, and sometimes there is some confusion about the radiometric temperature obtained from satellite and the 2 meters temperature. And it's important to highlight that although these variables are strongly correlated, they are not the same. And we have here 2 examples, one in southern Spain, an arid region, dry arid region, and the Black Forest diurnal cycle for these 2 variables. And we can see that they peak at different times. So LST peaks around noon, and whereas the 2 meters temperature continues to increase after afternoon. And the amplitudes are larger for drier regions because for vegetated conditions, the plants are controlling their own temperature through evapotranspiration. On the Landsat, the validation activities are quite important. So for a product to be released to the users, it has to fulfill some requirements, and validation is usually done by comparison with similar products from other platforms, like for the case of LST with MODIS, and with in situ data. And this is an example over the Netherlands. The left-hand plot shows daytime measurements, and the right-hand side plot shows nighttime measurements. And as you can see, there is a very good fit between the land surface temperature measured by Severi and in situ measurements, with a bias of -0.4 over daytime, and with no bias for this case during nighttime. The accuracy of the satellite retrievals, of course, it's not the same for all the regions within MSG, and this figure shows the error or the uncertainties for a given slot. We are providing these fields, the uncertainty bars, to the users to give them the ultimate decision on the applicability of the product, considering their own applications. And as we can see here, for quite a big area, the uncertainties are below 2 Kelvin, and they depend on the uncertainties on the input data, namely the emissivity, the water vapor content, the sensor noise. And for instance, if we go to regions with very high water vapor content and high view zenith angle, such as the case of the South America, we get quite bigger errors or uncertainties. And these diamond shapes figures here tend to illustrate what's the major contribution to the final product. of the inputs. So for instance, for the desert region in Africa, we have that the major contribution to the LST uncertainty comes from the uncertainty of the emissivity. This is an example I took from the Landsaf web page, where we have some applications to show how the products can be used. In this case, we have the example of a severe heat wave that affected Southern Europe in 2017. On the 3rd and 4th of August, and we have superimposed the maximum daily air temperatures on the animations, and it's easy to see that the hottest regions are coincident from although we are not looking at the same parameter. The LST and 2 meters temperature will be spatially coincident. So I think that's it for the LST. Christine, do you want me to continue?
Thanks very much, Carla. I just had a look on Slido. I cannot see any questions. Regina, did I miss anything?
No, we don't have any questions at the moment.
Okay, then if you still have questions, don't hesitate to put them on Slido, also if it is about LST, of course. But let me give you, let me tell you that we will also have a short course dedicated to land surface temperature data records. And this will happen next week on Wednesday, 19 May at 12 o'clock UTC. And if you go to training.eumetsat.int, you will find it under short courses. So if you're interested, register for this. But of course, you can also ask questions. There is actually now a question on Slido. Regina, can you put it up? Okay. Is land cover type incorporated into the LST dataset?
Yes, yes. For the estimation of the emissivity, we are using the fraction of vegetation cover, and this that I will be speaking about in the next slides. And this FEC product takes into account the land cover.
Okay, thanks very much, Carla. I don't see any further questions, and the slide will of course remain open, but I think you can now continue with the vegetation parameter.
I will start with the vegetation products, and this is the first parameter I will be speaking about is the NDVI, and this is the only polar orbiter satellite product that we have in the data cube. The basis for retrieving vegetation properties and conditions from satellite is the differential reflection of vegetation in the light, in the red light, and in the near infrared, what is known as the red edge. And we have here the spectral reflectance, also for healthy and for stressed vegetation. And you can see that for the healthy vegetation, this red edge is much more pronounced. And so we are expecting to have the NDVI higher for healthy vegetation than for stressed vegetation. Okay, so the NDVI from the Landsat is derived from AVHRR on board METOP in the 0.6 and 0.8 micrometer channels. And this data is converted to top of atmosphere, to top of canopy reflectances, applying a SMAC algorithm. And information about the water vapor content comes from ECMWF. We use the aerosol optical thickness from CAMS, and also ozone information from probe. This NDVI is available each 10 days since 2007. And the image here shows a year composite in 2009. Again, validation, this usually for almost all products, the strategy is the same. We compare with the other, with similar products from other platforms and within situ measurements. In this case, we have a map comparing the Landsat NDVI with NDVI from Copernicus, and we have the root mean square differences for all globe below 0.2. Then I moved to the suite of vegetation products, starting with the fraction of vegetation cover. This represents the fraction of green vegetation that is covering a unit area of horizontal soil, whereas the leaf area index takes into account the volume of leaves. So we'll have a higher value of leaf area index when we have more densely vegetated leaf. So these two parameters define the structural properties of a plant canopy. Then the fraction of photosynthetically active radiation, it's a product that takes into account the radiation that is good for the photosynthesis that is absorbed by the green parts of the canopy. So it indicates the presence of alive elements of the canopy. So it is more related to the health of the plants. All these parameters are available on a daily basis, and they have been produced since 2004. So the algorithms to derive these products, and this is very detailedly explained in the ATBDs, but to simplify, the FEC and leaf area index rely on an optimized spectral mixture analysis that consists of 3 steps. It first determines how many constituents are present in an image. So this is obtained from the prevalent land cover. We have the pairs of vegetated and soil end members in the image, and we from the when we do an observation, we will see how this observation falls into the space of the channel. So this is channel 1 refers to 0.6, and channel 2 to 0.8, and channel 3 to 1.6 micrometer. And the distance between the observation and the pairs of vegetated and soil will give the fraction of vegetation cover. FAPAR is derived from an NDVI-like vegetation index, so meaning that only 0.6 and 0.8 reflectance values will be used for FAPAR estimation. These graphs here show the comparisons with in situ data. Sorry, not with in situ data, sorry, with the spot vegetation for FEC, LI, and FAPAR. And we can see that the bias is quite small. There is a good correlation between the two variables. Of course, this is the best results are shown it seems to be for FEC. Then when we move to leaf area index, we have some underestimation from Severi for the case of high leaf area index values. Nevertheless, the bias is still very small, of 0.3%. And for FAPAR, the bias is a bit higher. But anyway, the products are operationally distributed, so they meet the target accuracy. Also, with the vegetation products, we distribute uncertainty estimates. And for the case of the vegetation products, for most of Europe and Africa, we see that the uncertainties are very low and become higher when we have higher cloudy conditions and for snow pixels. This example here is also taken from the Landsat website, and it shows FEC anomalies for August 2020 as compared to its average between 2004 and 2017. And we see here the regions of Bulgaria, Romania, Moldova, with very with negative anomalies of FEC. So here only negative values are shown in the map, because this was a drought that hit this region over August. And these products are interesting because we can follow the daily evolution. We can do a daily monitoring of the vegetation evolution. And we have here for a place in Moldova, a site in Moldova, the comparison of the actual FEC in blue with the reference, the FEC average for the period from 2004 to 2017. And we can see that although there are some days, some periods where the vegetation is green, after August, the FEC values come below the average, and they don't recover until the end of the year. Yes, and that's it for the vegetation products.
Yeah, now there are a couple of questions on the vegetation products. Regina, can you share them, please? Okay, first one is, can you briefly elaborate on the leaf area index retrieval algorithm? The spectral mixture analysis only gives you the fraction of each end member, say fraction of vegetation, but how is the leaf area index estimated?
So the spectral mixture analysis is the basis of the FEC retrieval, and the leaf area index. I would ask you to refer to the ATVD, where this is very well explained, because I cannot explain you in detail how this is retrieved. I'm not sure, maybe João, that's here in the session, maybe he can give a better answer.
No, I think I would recommend to go to the ATBD. It's a quite complex retrieval algorithm, so I don't think it's suitable to explain here.
Yeah. So please forgive us, we haven't prepared for all the variables here, the details of the retrieval. You may understand that. But if the need is there, we would consider also to do a short course going into the details of the retrieval of the vegetation parameters. I'm sure that could be interesting. But yes, we have all the documentation on the Moodle page. And if you have questions about that or want to discuss with somebody, so let us know, and I'm sure that colleagues at the Landsat would be very happy to discuss with you. Next question is, have you considered adding additional temporally static information on land use? For example, cropland, broadleaf forest, evergreen forest from Corinne land cover or soil type to the data cube. We have not considered that so far, Oliver. But it's an interesting suggestion. Okay, who is next? Yeah, we continue with Carla, and what's next on your list?
Evapotranspiration. So the reference evapotranspiration is the evaporation rate from a clearly defined reference surface. So what does this mean? This if you have a well-watered surface, that is for this case, it's a grassland, and so you don't have water stress, and you have the solar radiation driving the evapotranspiration, and so it's the ideal case. So this is independent of the crop type or development or management practices, and this product is available also from 2004 on a daily basis. And here is an example for the 17th of June 2018. So the retrieval, of course, you can find detailed information about the retrieval on the ATBD. It is estimated, as I aforementioned, from the daily global radiation. In this case, we are producing this product also in the Landsaf, and this is estimated from daily global radiations, as this is the main driver for the evapotranspiration over that ideal surface that I mentioned. The validation of this product is done only with comparing with in situ measurements, and this is an example over the Netherlands, Cabau, spanning for 5 years. And we can see there is a very good match between reference evapotranspiration from the Landsaf and the in situ measurement with the bias of 0.1 millimeters per day. And I think that's all. I encourage you to explore the data cube and get back to us.
That I would like to continue with how you can access the data cube. So for some reasons, we cannot provide you here publicly with the links to the threads server on which the data cube is provided. For this, we'd like to ask you to please enroll to the exploration phase, and you can do that on the Moodle page that we have mentioned quite some time now here throughout. And if you are on this page, you will see something like this. And here on the left-hand side, is an opportunity to create an account on the EUMETSAT Moodle instance. And if you have this, you can enroll yourself to the exploration phase of the DNV cube. And then you also have access to this part of the Moodle page, which has the link to the thread server in it. You can then just take this link. And one possibility to just easily get an overview and browse what's in there and how do the data even look like, but this is only a suggestion, would be using Panoply. This is a free and open source tool provided by NASA GIS. If you Google it, you can simply download it. And here you have the opportunity to open a remote catalog. And if you open this here, you could paste the URL of the thread server just here, load the catalog, and what you then see is the data cube. I had it open here for you to see how this looks like. Here I've used the example of the EUMETSAT Global Radiation Climate Data Record in monthly resolution. And this is just how the example map here looks like. You could browse through the different time steps. You can see here that this is monthly data, so you have one map available per month. But if you know any other tool, if you're familiar with other tools, I mean, most welcome. Just use what you have. This is just an example to easily browse and get a quick overview on what is actually provided in the cube. This is probably not the way you would like to really work with the data. For this, I am very well aware that you'd need something else. So if you go to if you paste the URL into an internet browser, you'll see this catalog, which is the same that you just saw on the Panoply, of course. And again, here using, this time I've picked the examples of the DNI, the direct normalized irradiation climate data record from the CMSAF, also in monthly resolution. If you click on that, you will see two subfolders. For all the solar radiation parameters from the CMSAF that are here, you will see two subfolders. One that contains the variable of question for all sky conditions, so the sky as it actually is, and one for the variable under assuming clear sky conditions, so no clouds. If you then pick one of the subfolders, you get, of course, one level deeper, and under this folder here, you will see all the individual files that are listed. In this case, you have one file per time step. But the more important link is probably the parent folder here. So if you click on this one, you will find the metadata information for this data record that you have here. So you see the data format, the data type. You will see who created the data record, which is the CMSAF in this case. The geospatial coverage, which should be the same for each of the variables in the data cube, and the time coverage of that particular data record we are looking at here. But most important, you can see the different ways with which you can access the data cube, and this is available for all the variables. So you can access it using OpenDAP, using WCS or the NetCDF subsets. These are all different ways that are available to you to subset and subsample your data. So you can make a selection for the region, or make a temporal selection of the data you are interested in. I'm not going into many more details for this one, because I would assume that most of you have their tools to work with the data. If there is more information required on this, then please let us know, and we'll provide it to you in due time, also on the in the section of the exploration phase for the cube. There are some R tools that you may want to consider to use when you work with this data. We made very good experiences with them, because they are both very convenient when it comes to working with time series to longer records. So we have two. One is the CMSAF R toolbox. This was designed by the CMSAF for use of their data, but it works for all CF compliant NetCDF data on a regular latitude longitude grid, which also have a time dimension. It's designed to work, it's designed for climate analysis specifically, so it contains many of the CDO functionalities, but translated into R. And an introduction will follow right now. And we also had a short course on this toolbox on 20 January this year. You can go back to the material. It is available on the EUMETSAT Moodle instance, and you will find a link on the Moodle page of the CUBE course. I will add that right after this webinar here, so you can check it out. Another toolbox is EUMETSAT. That is a tool that is really well suited for comparing gridded data with station data. So if you would like to compare the data in the cube with your own measurements or in situ measurements, for example, this is a tool I can highly recommend. And also for this tool, there is a tutorial on the Moodle page provided for you, and we have also material from a former short course that was held on 3rd February, but the tutorial that is provided to you at this moment on the Moodle page should contain everything that you need to know, and if you have specific questions, then please do not hesitate to raise them in the Moodle forum. But now let's have a closer look at the CMSAF R toolbox and what you could do with this. Steffen, are you there?
We have two questions, Christine. Do you want to answer them now?
Yep. Yes, please. Yes, the enrollment key is also shared on the Moodle page. You'll see that there. That's fine. And I will also provide it here on Slido below your question. There's another question for David. How does the soil water index compare to the Copernicus Global Land Soil Water Index product?
Yeah, that's a good question. I was wondering if you were referring to ERA 5 land, or whether you were referring to an observed product of the surface soil moisture. When it's ERA 5 land, there are definite similarities because they both use HTESL land surface model, but the HSAF version also assimilates data on top of that from ASCAT and screen level observations. But if you're referring to one of the observed products, the SWI, I think there are a number of them, then those are kind of referring to observed products at the surface, because the instruments can only observe at the actual surface.
Okay, so there's an ASCAT, so sorry if I just bump in.
Yeah, sure.
Question. So land.copernicus.eu, and then go to the global side. There's also a soil water index product. And that is actually also done from ASCAT in some way. So that's why I was wondering if you are in relation to them, but it's good to know you're not. So these are two different products, but in essence, I think it would be useful for end users to kind of understand what the difference is. At least you are better from a kind of to use it with ERA 5 or with seasonal forecast like I do. This is actually practical, your approach, that you have the same kind of products out. I like that because they have different, but many different options. So, but just check it out, and maybe at some point it could be added to the documentation. Thanks.
Yeah, sure. I know there are definitely similarities between some of the Copernicus and HSAF soil moisture products, and it's something we need to work on to make it more clear what the differences are. So yeah, thanks for that.
Okay, good. Then I suggest we continue with the introduction to the toolbox. Stefan, floor is yours.
Okay, can you see my screen?
Yes, we can see it.
Good, okay. So after the previous presentations, you might be a little overwhelmed now by all the different data sets and the features of the data cube. And I think you might ask yourself, how can I use all this cool stuff? So, and I think the CM.R toolbox might be a useful tool for you in this case. The CM.R toolbox is a set of R-based tools to work with NetCDF data, and it is combined with a nice graphical user interface, so you don't need any R or scripting experience to work with it. And the toolbox was developed within the framework of our CMSAF training workshops to have one easy-to-use tool for data preparation, data analysis, and data visualization. The toolbox is specifically made for beginner with satellite-based climate data, but I am sure that also climatologists from weather services or research institutes might have fun with it. And the toolbox is made for users with no or R scripting experience, like I said, but also people who know R or who want to script their jobs can use the toolbox and the functionalities of the CMSAF packages, R packages. And of course, the toolbox is made for users who are interested in SAF climate data. The toolbox is structured in three main parts. The first is the preparation part, so preparation of your data. So this means extracting, choose time and the region, and merging data. The second step, and most important, is the analyzer step. So here you can analyze and manipulate your NetCDF climate data by a huge number of different operators. And of course, in the end, you want to visualize your data and make some nice figures. And now I want to start a live demonstration. I was asked to do this. So keep in mind, that's live, everything can happen. So the only real R command you have to know is the run toolbox command to start your toolbox. And here you can see the main interface of the toolbox, which is divided in these three main parts: the preparation, the analysis, and the visualization. And I have to mention, I will present today the toolbox in its latest available version. So there will be probably some minor adaptations to work more easily with the data of the data cube. And as time is limited today, I think this will be more or less a kind of teaser, what you can do with the toolbox and how it looks. So the preparation step might be adapted to the data cube, similar to what you saw with Panoply. So we don't talk so much about this, and we directly start with analyzing some example file. For this, I chose the surface incoming shortwave radiation from the data cube from 83 to 2020 for Europe. So, and that's the main interface of the analyzed panel. Here you can see some short file information. You can see the longitude and latitude dimensions and the time dimension and the range of the included time steps. You can choose the variable. In this case, there is only the shortwave radiation included. And to make it a little bit easier to find what we are looking for, we decided to group all the available operators in several groups. So for hourly, daily, monthly, seasonal, you can see there's a lot of different options. You can do spatial operations, selections, data manipulations, or even simple climate analysis or compare data. And after, when you have chosen a group of operators, you can choose your operator. You can choose the output format, it's mainly NetCDF. And you have also the option to apply several operators one after the other. So maybe I show you a quite simple standard workflow. In this case, we start with the surface incoming shortwave variation from 1983 to 2020. Maybe let's say we want to select in the beginning, select the time period. So let's select the latest climate period from 1999 to 2020. We want to apply another operator afterwards. So in the first step, now we select just this time period. This will take a few seconds, hopefully. So I think we can use, if some questions arise, there will be some waiting points. And if questions arise, I think we can use these. So now we have one file was created, including the time period from 1991 to 2020. And let's say in the second step, we want to create monthly anomalies of this time period, and we want to directly visualize the results. So this application will take about a minute in my test, because the duration of these operations is mainly dependent on the number of grid points. So here we have whole Europe included in a spatial resolution of 0.05 degrees and 360 time steps. So it's monthly data. This will take about 1 minute. So the climatology is calculated in the background for every month and subtracted from each month to derive monthly anomalies. Maybe some questions? No.
At
Be a
the
little bit
moment,
patient.
I can't see questions on Slido. but
No,
this may
no
change.
questions at the moment.
Okay, that's the main goal of the toolbox, to make everything easily and it takes it as a good sign. Mm. Mm.
There is
So-
no question on Slido. Regina, you don't need to put it up because this would disturb Stefan, I guess. I just read it. Are there particular R libraries one needs to install in order to use the R toolbox?
Yes, there are. So the main library is the CMSAF-R package. And when you install the CMSAF-R package, all depending libraries will be installed with it. So that's the main one, the CMSAF-R package.
And further details to that are explained in the tutorial that is provided on the Moodle page again to the cube. Yeah, Stefan, please go ahead.
So what you can see here now is the monthly anomaly of the surface downwelling shortwave radiation for January 1991. And let's just visualize one example. I know that the May 2018 was, at least for sunshine duration, a quite we had a quite huge positive anomaly for this month. So we can have a look into the statistics of this month. You can see the maximum and the minimum values, and by this you can easily adapt your color bar to make it a little bit nicer. We can choose a different color scheme. Maybe here, red to blue. Wait a few seconds, because it's a lot of grid points. And you can see we have now a nice anomaly plot of the surface downwelling shortwave radiation anomaly in May 2018. You can see this strong positive anomaly in the northern parts of Europe, and also some negative anomalies here in the southern parts. And I'll show you one more option to make a nice plot. Let's say we want to visualize just one country. I'm starting with Germany. And here you have the same, so the corresponding anomaly for Germany. So here you can have a look into all the different options you have to make some nice figures. And I think it's yeah, have a look. We will have one more.
Stefan?
Yeah,
I'm just interrupting because there was a question on Slido asking what climatology does it use, or which climatology did you use as a background to calculate the anomaly that you've just shown?
In the last example, it's quite simple method to calculate the anomalies. So the climatology will be calculated from the whole time period, which is included in the provided file. So I provided a data file including data from 1991 to 2020. So the climatology will be calculated from this whole period. So the reference for the just presented anomalies is the mean from 1991 to 2020. So there, I will show you in if we have some time afterward, a different method to calculate the anomalies, but that's the easiest one here in the toolbox, where you can get some anomalies within a few clicks. Maybe one more example here. If you might be interested maybe also into station data, or let's say into a specific location. So for this, you can also quite easily select one single point. So I'm today in Frankfurt. I'm choosing Frankfurt. Now we're cutting the grid point of Frankfurt from the data set. You have here now a nice time series from 1983 to 2020. So for the whole time period for the location of Frankfurt. You can include, if you want to, a linear trend line, and you can also slightly increasing trend. You can also easily do an time series analysis, where you get here the time series, the monthly anomalies, including a trend line, the average seasonal cycle, and some other useful stuff. And in the end, I wanted to show you one more example. That's one of our latest additions, updates, and I find it quite cool. So that's the tab here, the climate analysis. In this, you can do anomaly plots, climatology plots, or I think this is a nice way to present the change in a variable over a long time period. This is inspired by the Ed Hawkins warming stripes plots. In this case, we have monthly data. I will do an annual plot. So we select the time range to 12. So every 12 months will be averaged. You have the option to select a specific country or a selected area, by which you can select by the longitude and latitude sliders. And here you have specifically the option to select your climatology. So here you can change the climatology like you want easily. So from 1991 to 2020 again. And now in the background, all the calculation stuff will start. I think it will take now maybe 3 minutes. So, and I think in this meantime, I can show you a few more highlights of the toolbox. So at the moment, there are more than 100 operators included in the analysis panel. So most of them are inspired by the known CDOs, so the climate data operators. And they are translated into R. So there's an option to download your results in multiple file formats. So if you like to visualize your results in your own tools, you can easily export the data as KML to visualize in Google Earth, or as GeoTIFF to use a GIS tool. There's an option to compare your data with other satellite or even station data. And there are many, many options to visualize your results in a nice way, I think. There are, like I showed, the climate analysis plots can be created by just a few clicks, and you can make some quite nice investigations using these plots. Here you can see, for example, the sunshine duration anomaly for 2020 for the whole year, and you can see that 2020 was the third sunniest year in the time period from 1983 to 2020. The toolbox is also able to be used remotely by just clicking an URL. I hope we can implement this in the near future. And if you need help using the toolbox, have a look at our manuals, YouTube videos. We have a toolbox paper. There's a question and answer document, cheat sheets, flyers, and a lot of more stuff. And you'll find all this stuff on our toolbox website. Or if there's something which cannot be answered by all this material, just contact us via our user help desk. So let's see if we... Oh, it's still calculating, so we have time for more questions.
Yes, and there are actually a few questions on the Slido, but now I think, for the sake of oversight, Regina, if you could share the Slido, please.
Oh, I should.
Okay, first question is the toolbox limited to EUMETSAT data, or can it be used for any CF compliant NetCDF data?
So in principle, it can be used for any CF compliant NetCDF data. Like Christine said, the data have to be on a regular longitude latitude grid, and they have to have a time dimension.
Okay.
But it was already used for several other types of data.
Is it possible to adapt the algorithms behind the EUMETSAT toolbox, for example, changing mean to median?
That's possible if you have a little knowledge in R. Yeah, all this code is open source, and you are invited to contribute to the development if you want to. Yeah.
Okay, I guess that's another question to the climatology you showed earlier or calculated earlier. Can the climatology period be customized?
Yes, of course. The first method I showed is the most easiest. So just one click, more or less, or 2 clicks. And there are also, of course, the options. You can calculate your climatology separately for the time period you want to have, and then you simply subtract the data. Or like I showed in the last example, there's this climate analysis panel where you can choose the time period of the climatology.
Okay. Next question is, are the products made in this toolbox exportable as a picture or time series or CSV, etc.?
Yes. Yes, I showed you there are several different formats where you can export your data. You can export your time series as CSV data, as NetCDF. You can export pictures in PNG, JPEG, and PDF. And there's also the option for exporting KML and GeoTIFF. And of course, every result is stored as a NetCDF file in the output folder.
Okay. Then can we run the toolbox in your cloud system, or do we have to download the data and run the toolbox on our own workstation or PC? At the moment, you have to download the data and work with the toolbox, but we are at this moment working on a solution so that you can access the cube or any remote catalog directly from the toolbox, as Stefan just mentioned. That's work in progress, but we hope that we can provide it to you in the not too far future. Stefan, back to you for some last comments.
Hopefully,
and then...
Oh, I have to share again. Yeah, the result is ready. Now you can see a nice but a little varying result. So you can see the increase in the anomalies, in the annual anomalies of the surface incoming short-wave radiation from 1983 to 2020. I think that's a nice result you can easily produce with the toolbox. So that was my last example. If you want to see anything else, I can do it, but I wasn't sure how much time is available.
Yeah, actually, we need to watch the time a little bit because we are running over by some 10 minutes. So thanks very much, Stefan. And of course, you can ask your questions about the toolbox or get in touch with Stefan at any time throughout the exploration phase. So don't hesitate to get back to us. And yeah, ask if you have questions or would like to simply have a discussion. That's also possible. Okay, but now we would like to see what Meteor Swiss has done with satellite data for climatological drought monitoring in Switzerland. And I welcome from Meteor Swiss Anke Duguay-Tetzlaff and Ann-Kathrin Burgstall to tell us more about what they have done and how they have used satellite data to monitor drought. Anke, Ann-Kathrin, whoever is starting, the floor is yours.
Hi, everyone. I hope you can hear me and see my screen.
I can hear you and I can see your slide. Yes, it works.
Perfect. So a warm welcome also from my side. My name is Ann-Kathrin Burgstall, and together with my colleague Anke Duguay-Tetzlaff, we are very happy to represent to you today the small feasibility study we did on climatological drought monitoring in Switzerland using sub-satellite products. So we did this feasibility study with the help of ETH Zurich, TU Wien, and the Belgium Weather Service. And I have to add here that we did this study before the data cube was available. So we still had to deal with some of the issues that I'm sure with the data cube are now perfectly resolved. So to start off, I'd like to give you just some short background information. Anke and myself, we work in the climate division of Meteor Swiss, and thereby we are especially interested in the climatological or the temporal evolution of drought events, looking at time series, for instance, to see how the different drought events are depicted in different data sets. And to give you a short overview of what we already have available at Meteor Swiss for our drought monitoring, I just show you here some plots of the indicators we already use operationally. So we, for instance, have implemented the standardized precipitation indicator or the standardized precipitation evapotranspiration index, which I'm sure you know. We also already look at the water balance, and apart from these rather temperature and precipitation based indicators, we also have indicators available operationally, which are based on soil water models. So for instance, we look at the soil water deficit, an index called the arid drought index, and also at the soil moisture index. But I don't want to go into more detail here. It is just important for you to know that all these indicators are solely station-based. So, so far we only have localized information available on droughts, and spatial information on drought events is still missing. And here is where our small feasibility study comes into play. So in the study, we looked at several satellite-based products and compared it to both station-based modeled indicators and also to measurements to see if they show anomalies at the same time, for instance, and how they match in general. And how or which climatological, which satellite-based indicator would be the best to complement our station-based drought monitoring at Meteor Swiss. So first of all, I'd like to introduce to you the different data sets that we used in our feasibility study. And I'd like to start off with the satellite-based products. So first of all, what was important for us from the climate division is that we have long time series available. So with long, I mean at least 10 years of high quality data. Another important thing for us is that we have the data available open source and operationally. So in this short overview here, you see that we used in our feasibility study kind of 4 different drought parameters. So we looked at a soil moisture product, we looked at evapotranspiration products, We also considered land surface temperature, and we looked at different vegetation products. And for more detailed and more technical information, I'd like to give the word to my colleague Anke, which provides you here with more information.
Yes. Thanks, Ann-Kathrin. This is Anke speaking. Yes, a year ago, my colleagues, Ann-Kathrin, came to me. Anke, you're a satellite expert. We would like to use satellite data in Switzerland for climatological drought monitoring. Which data can you recommend to us? And the first data set I recommend to analyze is this HSAF ASCAD soil water index data. To make the confusion completely complex, I recommended Ann-Kathrin to use a high resolution data, which, if I understand it correctly, is not available on the data cube, and which is very close to this the data set which is available via the Copernicus Climate Service. But this is also an ASCAD product. The only difference compared to the product is that it's 500-meter resolution. This product also has information on the soil moisture root zone, water vapor, and it gives a kind of estimation on the soil water with the depth by integrating the ASCAD soil water or soil water measurements with the time. So this was a very short introduction. And next slide, please. We also had a closer look at the different Landsat, METEOSAT evapotranspiration products. Carla has given a very nice introduction to those products today. I just want to mention what is very nice for us in Switzerland. This data have a 3-kilometer resolution. This is suitable to depict some nice pattern in Switzerland. We had a look at this potential evapotranspiration data Carla introduced, but we also had a look at the real evapotranspiration. This is a product which, if I understood it correctly, is not yet available via the data cube, but we thought it's very interesting for climatological climate monitoring in Switzerland, because we have strong indications from the ground measurements that this is actually the driver for the climate change we observe. So we see more drought events in Switzerland, and our station-based data indicate that it's not the rain pattern which are changing, but it's actually the evaporation which is changing. And I also said in this slide here, it's the CMSAF and Landsat METEOSAT evapotranspiration data, because I just want to inform you that in the CMSAF, we closely cooperate with the Landsat at the moment, and there will be a new release in 1 year, where we extend this climate data, which are now available until 2007 in the data cube. We extend those data back to the 80s. And as we are the producers of this data, we just had a very first look also to the long time series. Next slide. We had a look at the EUMETSAT land surface temperature data, at the METEOSAT land surface temperature. You find the METEOSAT land surface temperature data record in this cube. This is the Landsat land surface temperature data record, which goes back until 2007. In the CMSAT, we also work very closely with the land surface temperature, the last phase, and also this phase. And we actually have released an even longer climate data record, which is not available in the cube yet, which goes back to 1983. We have a slightly different retrieval, but we try to be as close in quality as ever we can to the Landsat data. So you can, when Ann-Kathrin is analyzing this data today, you might even expect a better performance of the Landsat data. They have more modern satellites. And I recommended those data to Ann-Kathrin because they are now available for about 30 years. Those are hourly data. And on accuracy and precision, we are very confident that we have a good climate data record here. The same holds for the Landsat. And also in terms of stability, I told Ann-Kathrin I would not look at absolute trends. But if you just want to compare your drought years with the non-drought years and to see if you have an anomaly, I'm pretty convinced that this will help. So next slide, please. And we also had a look at the vegetation health index, which is commonly used for drought monitoring with satellite data. And this vegetation health index, it's a WMO index. It combines land surface temperature with vegetation. Here we use the CM-SAF land surface temperature because we are really interested in long-term climate data records. Because this is the NOAA vegetation, because the NOAA vegetation NDVI data go back to 1983. But of course, if you're just interested in shorter periods like 2007, you can do a similar analysis using the data from the cube, using the Landsat land surface temperature and also the Landsat NDVI, which Carla has introduced. And now I give the word back to Ann-Kathrin.
Thank you, Anke. So now that you know which satellite products we used, I also want to introduce to you quickly the drought indicators that we used or that we have available station-based. So first of all, we used for the comparison an indicator called soil moisture index, which is a modeled soil moisture a modeled soil moisture indicator which assumes a soil with average properties and a grass surface. So we assume dense grass and a 40 centimeter root zone. And this indicator is based on meteorological parameters only. So it considers precipitation data, temperature, radiation, relative humidity, and wind. And behind this index is a relatively simple bucket model. So it considers daily inputs and outputs. Precipitation fills the bucket, so to say, and evapotranspiration removes the water. And in case the bucket is full, so when the soil is saturated with water, then precipitation no longer enters the soil, but surface runoff occurs. So as an output, we have evapotranspiration, runoff, and also drainage in the model. And this is how this soil moisture index is then approximated. Apart from these soil moisture index, we also have available measurement data from the Swiss soil moisture experiment. And this called Swiss SMAX experiment, this is coordinated by ETH Zurich. So we got the data from ETH Zurich, and they have since 2008 they measure the soil moisture at 19 different measurement sites in Switzerland. They are mostly grassland sites. And the soil moisture data that we used in our study, that's integrated over a 50 centimeter soil depth. And apart from these soil moisture measurements, they also have installed lysimeters and mini lysimeters, where they measure at these sites evapotranspiration. And you can see here at the bottom right here the picture of such a mini lysimeter. So now that you know which data sets we used for our comparison, I also like to show you some of our first results. And I'd like to start off here with these two maps showing the high resolved HSAF A-SCAD soil water index that Anke just introduced to you. And I show you here two single days from 2015 and 2018, where Switzerland was heavily affected by drought events. And you can see here on this lighter green color that especially the northern alpine foreland was especially affected by the drought events. In 2015, it was also the Ticino part, so the southern part of Switzerland, which was heavily affected by the drought. And we now compared these ASCAD product with the MeteoSwiss soil moisture index, which we have available station-based. And this comparison I show you here in these 4 single plots. They represent the time series from April to October for 4 different sites in Switzerland, for Basel, Bern, Geneva, and Stabio. And at the bottom line, you see the year 2018, and in the upper line, the year 2015. So the heavy drought years, so to say. And we can see here quite nicely that the satellite product and the soil moisture index, so the modeled product, they correlate quite high with 0.6 or even higher for Geneva and Stabio. So this was already a quite nice result for us to see that, yeah, the satellite product here correlates or agrees so well with the with our soil moisture index. Apart from this comparison, we also compared the satellite ASCAD product with the measurements that we got from the SwissMax, so from the ETH measurement sites. And we compared these in terms of the anomalies. And I'd like to start off here with showing you the soil water index anomaly mean. Averaged over 10 different measurements sites. And what you see here in the gray area is the climatology over 8 years. And you see here the 5th to the 95th percentile. And the black thick line gives you the median over these climatology. And highlighted here in red is the drought event 2018, and in purple or pink, you can see the drought event in 2015. And what is seen here quite nicely is that these, for instance, if you follow the red line, that these heavy drought events are depicted quite well. So they show extremely negative anomalies here in the soil water index. And if you now look at the measurements, so at the SwissMax measurements for the same sites and for the same time period, we also see here quite nicely these negative anomalies for the drought years 2018 and 2015. And if you, for instance, also follow here the red line, you see in both data sets that we had for instance, in May 2018, a very negative anomaly also during summer. And then there's another negative peak in November 2018, also in both data sets. So they also seem to agree quite well. Exactly. So far to the soil moisture data set. Now, as introduced before, we also looked at evapotranspiration data. And I'll show you here the time series from 2009 to 2020. And you see the 2 satellite products, the EUMETSAT potential evapotranspiration and the actual evapotranspiration in red and pink. And the measurements from SwissMax are shown here in blue for the large lucimeter data and in yellow for the mini lucimeter, which are only available from 2016 onwards. But we see here very nicely that they agree very well throughout this whole time period. And what we also did was to look a bit closer in the annual course of the data sets. So what you see here is always the thick lines show you the median values, and in the shading gives you the 5th to 95th data range. And also here we see in this annual course that they agree very well. It's just that maybe you could see here in spring that the satellite product overestimates a bit the measurements, but apart from that, it agrees very well. This is here for the actual evapotranspiration. We also looked at the potential evapotranspiration. So it's basically the same plot, just the pink line is different. So now the EUMETSAT potential evapotranspiration is shown here, which is of course a bit higher than the actual evapotranspiration in the plot above. Last but not least, we also checked different heat and vegetation indices based on the CMSAF land surface temperature and the NOAA NDVI. So here again, I show you the maps of Switzerland, showing you in the upper left part, the vegetation health index, which combines the vegetation condition index in the upper right part and the temperature condition index in the bottom left part, and also you see the land surface temperature, always for 1 week in 2018, where Switzerland was also heavily affected by drought. And again, we see here that the northern alpine foreland is especially affected by these dry conditions. Now we looked at these data sets also in terms of their anomalies. Here you see the anomalies compared to monthly averages. And always when the color is brown, we have negative anomalies, and in green you have positive anomalies. And this is here for an example site in Bern in Switzerland. And what can be really nicely seen here is that the satellite shows strong negative anomalies for the huge drought events in Switzerland. So they are well depicted here. Last but not least, I show you here a short summary slide of most of the data sets we just talked about. Again, they are compared in terms of their anomalies. So you see in gray, again, the climatology. In dark gray shading, you see the 25th to the 75th% data range. And in light gray shading, you see the 5th to the 95th data range, and the black line shows you the median. And highlighted are again the extremely dry years, 2015, 2018, and also 2003 here. And these anomalies are always averaged over 4 sites at the Swiss plateau, where we've just seen that Switzerland is mostly affected by the drought. And of course, they don't fit or agree perfectly. Of course, they are also different parameters, but in general, we see that the dry events, they always show negative anomalies, or they are all well depicted in all the data sets, which was very nice for us to see in this first small feasibility study that we did here. So to sum our results up, we could see that the HSAF soil moisture data, they agree very well with the modeled soil moisture index, which we already use operationally. And they also agree well with the measurements from the SwissMax ETH project. We could see for the CMSAF and LST evapotranspiration data that they are also in good agreement with the SwissMax measurements. And we could also see that the drought events are well depicted in the combined CMSAF land surface temperature and the NOAA vegetation products. So overall, we could see that the SAF satellite products can really well complement the station-based indicators for drought monitoring in Switzerland with the still missing spatial information. And with this, I'd like to thank you for your attention, and now I'm happy to take any questions. And also, in case you have later on any questions, you can always contact me via this email address here. Thank you very much.
Thank you very much, Anne-Kathrin and Anke. And we are waiting for some questions on Slido, or if you rather want to speak, then you can raise your hand and we can give you the microphone to ask some questions. Maybe in the meantime, Anne-Kathrin, what were your say that the biggest challenges you had to face or to solve while working on this project?
Yeah, so actually there were quite some, because it starts off when you try to find available data sets. So first of all, of course, you have to think of, okay, which data sets are available? Are they available operational? How do they compare? How do I get to the data? And we were lucky to have very good contacts to our data providers, but still, it cost some time to do this first thoughts. And then, of course, you always you have to do with different data formats, with different grid formats, and different temporal resolutions. So you have to do the aggregation and so on. And I guess now with the new data cube, or just as I saw with the live R, it was really nice to see that. I think now it goes much faster to do this kind of analysis. It's nice to see that it will soon be available.
Thank you. There are still no questions on Slido. I guess people may just be a bit tired, because I can't believe that there are no questions. But now questions are coming in. Okay, Regina, would you mind sharing? Okay, now they're coming. Okay, is there a publication for this study already?
So this is what keeps me busy nowadays, now at the moment, actually. So we're working on a publication on that. Definitely, yes. There will be a report or also a peer-reviewed paper. We haven't decided yet, but there will be an online available publications hopefully soon. Yes.
Okay, and would you mind sharing then the link with us once this is available, so we could share it with participants? Yeah, that would be nice. Do MeteoSwiss use any of the satellite data for operational near real-time drought monitoring?
So far in our group, we don't use satellite data operational for drought monitoring. That's what we are currently trying to change, or really want to change, to complement our station-based drought monitoring with spatial information. But so far it's not done operationally.
Okay. Another question that refers back to one that was asked earlier. Sorry for repeating my question, but did you see influences of forest coverage on data quality? I assume your station sites were located at different land cover types, or just agriculture?
So our measurement sites, or the sites we looked at, they are actually mainly grassland sites. So we did not look into to any detail here. So we chose mainly grassland sites. Also from the Swiss Max measurement sites, they are all grassland.
Okay.
That we used. Yeah.
Okay. Then I maybe would like to ask the audience: have any of you ever done any validations with satellite-based soil moisture data for forested areas? Are there any experiences? Looks like there is a bit of a gap, maybe. You could raise your hand if you would like to comment on this. We will keep the questions anyway, so we can come back anytime, but if it happens that there is somebody in the audience. Yep.
Okay. I did raise my hand, so I wonder why.
Sorry, did not see it.
Okay. Anyway, so two things. I can first answer also your question. So in FMI, so I have not been directly involved, but my colleagues have done these soil moisture product validations in Sodankylä. In Lapland, we do have a network of soil moisture stations that are both in forested areas, they are in open peatland, they are in whatever. There are at least 6 different cover types, and there are issues exactly with these kind of forested stations, that they are not as well kind of matching to the retrieval systems. But details, I think Jaakko Ikonen probably is the name that you could go after. I can put it into the Slido. Just comment in general that thank you for Ann-Kathrin and Anke. This is a nice example, but I'm looking at this from a point of view of that those kind of actions we want a lot, that the data cubes and why to put this on the web browser anyway for anyone to do. The point is not necessarily that it's just the weather service or researchers in our domain, which I think we all get things done anyway. But the point is, how can we make it really easy for other people, companies, small ones, to also do similar things like this? I think that's what I'm looking for, and I do see that the CM-SAF kind of are good examples of this can be done and promoted. I do see, and this is maybe then the comment to Meteo Schweiz, use the German word as I'm half German. It's nice that you have many options. Anyway, the point is that these solutions that you have is also, I think, one of those things that we really should talk about and keep up, that the applications that we do, we should also try to make open source available for others, because that would also make it much more faster to get many people use these. And the great thing about these data cubes that are probably with global data is that even if one of us does it for a certain country, if the code is there, the data is similarly available. It's like it's a minutes kind of job to do it wherever else. And I think that is the great thing that we should look for. And we will get there. I do see that. Thank you very much.
Thanks very much, Mikko. Very valuable comment. Thanks for that. Are there any further questions or comments at the moment? At the moment, I cannot see them. So I take back the screen to show you how we envisioned the exploration phase and how we think that should look like. So what is the exploration phase all about? The exploration phase is, I think, the most important step in that pilot project on the data cube. The exploration phase is mainly for you, our hopefully users, for you to check out the cube, to check out how does it work for you. At the same time also to get help and support. So again, please enroll to the exploration phase, and then you can use the Moodle forum and everything and get in touch with us to get help and support, also to collaborate with each other. So please use the opportunity. And of course, to provide feedback to us, to tell us how is this useful. And thank you for your comment, Mikko. I think this is also a bit of the question about who is doing what, and if people are providing services with, like, making global drought indices available, how do we as a satellite data provider, what is our task in that? How do we need to provide the data to make your job as easy as possible, or as impactful as possible? And then it is also, we really take your feedback serious, and we'd like to find out how, if the data cubes are appreciated, and how we could do better in serving you better. That's also a learning curve for us. But the more input we get from your side, the more impact this will have on EUMETSAT for sure. So how can you participate in the exploration phase? The first step is to enroll for the exploration phase. So if you go to the Moodle page, maybe Regina, you can post the link again into the chat. You find a little box that looks like this, where you can create an account on the EUMETSAT Moodle instance and then enroll yourself by using this enrollment key. We will also send all this information in an email after this webinar, so you will have the links in any case at hand. Then test the cube, use the forum once you're registered for the exploration phase, You also have a forum available that you can use for questions all around the cube while working with it. What we will do in addition for people who want to do that, and for all the participants of the exploration phase, but only if you wish to do that, to share your experiences in form of a document on SharePoint. So I have created already a folder on SharePoint that I will share the link with all the participants of the exploration phase, so you can upload material that you have created. You can share a little Word document where you maybe would like to share a little project that you may have worked on, or that you are starting to work on. This is also a nice way to collaborate. I think it's a way to collaborate, and also a way to provide us with feedback on this. Then you can join the live touch points, which we have scheduled throughout the month of June and July at different times during the day. Maybe you can make a few of them. Maybe you can even make all of them. The agenda is not yet fixed for these live touch points. So this will also be based on the questions and feedback we get from your side. So we try to address your questions, of course, as soon as possible. We try to get back to you. I will have an eye on the Moodle forums all the time. I will be your first level support, and whatever I cannot answer, I will ask my colleagues to provide you. And the frequently asked questions we will be dealing with also in the touch points, but you will also have the chance, if you let us know in advance, to present what you have done so far, and if you like to share your experiences with the cube. So the links to it will again be Zoom meetings, but it will be meetings, not webinars, so it can be more interactive. We will provide that to all enrolled participants. As soon as you are enrolled, you will get the information. And then as a participant of the exploration phase, you will have the chance to present your work at a meeting that we are organizing later in the year with a group called SALGI. This is a group who have collected quite a lot of experiences in working with satellite data on land surface observations, focusing on Eastern Europe, but now they are triggering more and more interest. And they have been working with SAF data and EUMETSAT data for quite some time, and they are meeting every 2 years. And so they are meeting this year as well. And during this meeting, we have foreseen one session on the data cube, and you would have the chance to present your work and your experiences with the cube also there. The meeting will probably be in December. The dates are not fixed yet. It will be about 3 days in September, and we will of course also work online. Are there any questions on the exploration phase so far? I see already some ideas for projects in Slido. It would be great if you could share your ideas then also on Moodle or on SharePoint with us. So step 1 would be a registering for the exploration phase, and then you will receive further information on how to collaborate and how to actively participate in the exploration phase. I do not see any further questions. I guess it's now really becoming time for lunch. One last thing I would like to ask you to do is please give us your feedback about this information day, so about the last few hours that we have spent with you. It's also on Slido. If you go to polls, there are some questions provided for you, and if you could give us feedback using this poll, that would be really very, very much appreciated. And with that, I'd like to thank all participants for joining in. I hope this was useful for you. I would like to thank all my colleagues who have helped me and supported me very actively in making this the cube happen and in making this information day happen. So thanks to to all the speakers and to the CMSurf, Landsurf, and HSurf particularly for supporting us. Thanks also for MeteoSwiss, to Anke and Ann-Kathrin for sharing their experiences. That's really very much appreciated, and I hope that we can talk about more examples of using satellite data for drought monitoring or vegetation monitoring in the next month. If you have any further questions and you don't want to use the Moodle page, you can also send us an email to training@eumetsat.int and we'll get back to you as soon as possible. And with that, I wish you all a nice rest of the day, and I really hope to meet you throughout the exploration phase and to see you also at the touch points. Thanks very much, everybody, and enjoy the rest of your day.